In the previous video, we studied numerical measures of center. In this video, we'll look at parallel numerical measures of spread, namely IQR and standard deviation. I'll also show how to interpret box plots, which are another visual representation of center and spread. Quartiles and IQR are tools for measuring spread. Quartiles are a companion to the median, meaning that they're computed in a similar way, and that we would use quartiles to measure spread for data where we are using median to measure center. To compute the quartiles, we first compute the median. Then, the lower quartile, or Q1, is the median of the lower half of the data. Similarly, the upper quartile, or Q3, is the median of the upper half of the data. Note that the lower quartile then gives the cutoff for the bottom 25% of the data, and the upper quartile gives the cutoff for the upper 25% of the data. The interquartile range, or IQR, is the difference of the upper and lower quartiles, and measures how spread out the middle 50% of the data is. Here's a visual representation of these ideas, using the earthquake data we saw earlier. For this data, Q1 is 6.6, meaning that 25% of earthquakes have a magnitude less than 6.6, and 75% have a magnitude greater than 6.6. So the blue area on the left represents 25% of the area in the histogram. Q3 is 7.6. Then 50% of the area of the histogram is between 6.6 and 7.6. We get an IQR of 1, reflecting that the middle 50% of earthquake magnitudes differ in magnitude by no more than 1. Let's work through these computations using the bird count data. There were 21 values in this data set. Here, I've shown the data in order from smallest to largest. Recall that the median is the middle of this list, which turns out to be 166. To compute Q1, we focus on the bottom 10 values. The middle of this portion of the data is between the 5th and 6th value. Since this falls between two values, we take the midpoint between them, or 158.5. To compute Q3, we follow a similar process, but focus on the top 10 values. The midpoint of this portion of the data is between 181 and 183. So we get Q3 is equal to 182. Then the IQR is 182 minus 158.5, which comes out to be 23.5. So far, we focused on histograms to visualize distributions of numerical data. Another visualization tool is the box plot. A box plot is a visual display of the key features of a distribution using median and quartiles. A box plot has a box in the middle, where the center line shows the median, and the edges of the box show the upper and lower quartiles. Whiskers are added at each edge of the box to show the minimum and maximum values in the data. There's also a standardized process for determining outliers using a box plot. I'll come back to that at the end of the video. Here, I've created a box plot for the bird count data. As we previously determined, the median for the data is 166, which is shown in the middle of the box. Q1 at 158 is the left edge of the box. And Q3 at 182 is the right edge of the box. The minimum value is 152. The maximum value is 228, but this is marked as an outlier. The next largest value is 206. Comparing the histogram and the box plot, we can see that the median does a reasonable job of measuring the center of the distribution. Note also that the box plot shows the right skewness that we see in the histogram. This shows up in the fact that the right side of the box is wider than the left side. Since both sides of the box represent 25% of the data, a wider box shows a wider spread. Similarly, the right whisker is longer than the left whisker. I've also included a box plot for the reservoir level data. This box plot shows the median reservoir level was approximately 70% of capacity. And the middle 50% of reservoirs were between about 48% and 82%. The box plot also shows the left skewness of the data. So far in this video, we focused on using quartiles to measure the spread of a distribution. An alternative approach is the standard deviation. This measure of spread is a companion to the mean, meaning that it is computed in a similar way and that we would use the standard deviation to measure spread for data where we're using mean to measure center. I've written the formula for standard deviation to give you a sense of how this is similar to the computation of the mean. X bar is the mean for the data, and X represents different data values. The sigma is the sum symbol. In this formula, we compute the differences between each data value and the mean and sum those differences. It then divides by basically the total number of differences. Taking this interpretation of the formula, we can think of the standard deviation as an average deviation from the mean. Although I've provided the standard deviation formula here, I won't ask you to compute standard deviation as part of this class. An important note is that just as the mean is not a good measure of center for skewed data, neither is the standard deviation a good measure of spread for such data. Here's a visual of the standard deviation. The red region represents data that is within one standard deviation of the mean, which is a majority of the data values. The green region shows 2 standard deviations from the mean, and the blue region represents 3 standard deviations from the mean. Comparing the two different histograms, we can see that the data on the right is more spread out than the data on the left. This will correspond to a larger standard deviation. But do notice that they have similar distribution across the different colored regions. This is true of symmetric distributions with a single peak in general. Statisticians and scientists take advantage of this to use standard deviation as a kind of ruler for comparing different distributions and values within a distribution. To see some example calculations, let's return to class exam scores. Note that these distributions have a single peak and are roughly symmetric around this peak, so mean and standard deviation are appropriate measures. In the data shown on the left, the means are different, reflecting different centers for each data set. However, the standard deviation for the 3 classes are similar, showing a similar spread. Now consider the data shown on the right. Here, the center or typical value for each class is similar. We can see this in the similar values for the mean. Now look at the standard deviation. It is largest for class F, which visually has the largest spread. The standard deviation is smallest for class D, which visually has the smallest spread. In this video, we've looked at 2 ways of understanding what the typical variation in the data is, the IQR and the standard deviation. Since they help us understand what variation is typical, they're also useful for determining what variation is not typical. That is, they can help us identify outliers. Here are rules of thumb that are commonly used. A value that is more than 1.5 times the IQR below Q1 or above Q3 is considered an outlier. Alternatively, a value that is more than 2 times the standard deviation above or below the mean is considered fairly unlikely. This corresponds to values outside the green zone. A value that is more than 3 times the standard deviation above or below the mean is considered highly unlikely. This corresponds to values outside the blue zone.